very important theorem. Let A be an m by n and P be L by n matrices. Then we have to prove that row space of PA is a subset of row space of A, and row space of PA is equal to row space of A if P is non-singular, right? So let's start with the proof. Let P matrix be as Pij, which is your L by M matrix, and let's take A to be as Aij, which is M by N matrix. And because the number of rows are m, so I'm writing this matrix in the form as R1, R2 up to Rm, right? Then we need to have the product PA. So this PA is equal to, this is P11. In the matrix form, I'm writing this P. So this is P11, P12, up to so on. How many columns are there? M columns. So writing here P1M. That is the first row, mth column, right? And then the second row, writing the second row, first column. Then is second row, second column. So on, second row, mth column. Likewise, if you write all these elements, at the end we will get how many rows are there? L rows are there. So, Lth row, first column. Lth row, second column. So on, Lth row, mth column, right? And writing this A matrix as R1, R2, so on up to Rm. Now how to multiply the matrices? Just take first element from first row and first column. Multiply this with R1, right? So you get P11, R1. Then take its sum with P12, R2. And so on we get P1M, Rm. And then taking the first element from the second row and the first column, that is P21, multiply this with R1. So this is P21 R1 plus P22 R2, so on, P2M Rm. Likewise, this is PL1 R1 plus PL2 R2, so on, PLM Rm, right? And now you have noticed over here that the first element of this matrix is a linear combinations of R1, R2 up to Rm, and second element is also the linear combinations of R1, R2, R3 up to Rm, and similarly the last element, right? Okay. Now, as the rows of PA are the linear combinations of R1, R2 up to Rm, right? Which means these rows will now belong to row space of A. Why? Please look it over here. Row space of A. Row space of A is generated by R1, R2, R3 up to Rm, right? Now, it is a property of the generating set that if V is an element belonging to Ra, here Ra is your vector space, right? So V belongs to this vector space if and only if there exist scalars such that this V is a linear combinations of R1, R2, R3, Rm. That is the generators of Ra, right? If V can be written as the linear combinations of the generators of Ra, then this V must belong to this Ra, right? So from here we can say that the rows of PA are the linear combinations of R1, R2, R3 up to Rm. So as these are the linear combinations of the rows of A, which means all these rows of PA will belong to Ra, right? So consequently these lie in the Ra, and because rows of the PA are belonging to the row space of A, so we can say that row space of PA is a subset of row space of A, right? Because all the linear combinations are belonging to the row space of A. right? Okay. Next, the second part. Now, just now we have proved in the first part that row space of PA is a subset of row space of A, where your P is L by M matrix here, right? Please mark this as 1. Now required to prove that row space of A is a subset of row space of PA. Then from these two results we can say that row space of PA is equal to row space of A, right? So I can write row space of A as row space of IA, yes, where I is your identity matrix. Because it is given to us that P is non-singular matrix, so P inverse exists. So I can write this as further, yes, instead of I, can I write P inverse P? Is it fine? Yes. So further this is equal to, let me take this PA together. So this is row space of P inverse PA, right? Which is further the subset of, yes, just use the first result. First result says that row space of PA, this A is a subset of row space of A, right? Where P is your L by M matrix. Here, row space of P inverse PA is a subset of row space of PA, yes, where this P inverse is also your L by M matrix. If P is L by M matrix, its inverse is also L by M matrix. So I have used the first result over here, and this implies row space of A is subset of row space of PA. Please mark this as 2. So from 1 and 2 we get row space of PA is equal to row space of A. Hence proved. Thank you.